Okay, so I fucked it up. I accidentally rebooted my PC. And let's hope the session was able to restart. Fuck.
Okay, why do I want this projection? Well, so why project? Well, so for capital P, which is the matrix. Good, good. Okay. Now I want the same result as the first projection. Okay. So that's the same result as the first projection. Here, I take any vector B, I multiply it by my projection matrix, and that puts me there. So this is PB. And now I project again. What happens now? What happens when I apply the projection matrix a second time to this? So I'm applying it once, brings me here, and the second time brings me, I stay put, right? The projection for a point on this line, the projection is right where it is. The projection is the same point. So that means that if I project twice, I get the same answer as I did in the first projection. So those are the two properties that tell me I'm looking at a projection matrix. It's symmetric, and its square is itself, because if I project the second time, it's the same result as the first projection. Okay, so that's, and then here's the exact formula. When I know what I'm projecting onto, that line 2A, then I know what P is. So do you see that I have all the pieces here for projection on a line? Now, and those, please remember those. So there are three formulas to remember. The formula for X, the formula for P, which is just AX, and then the formula for capital P, which is the matrix. Good, good. Okay. Now, I want to move to more dimensions. So we're going to have three formulas again, but you'll have to, they'll be a little different because we won't have a single line, but a plane or three-dimensional or a n-dimensional subspace. Okay. So now I'm moved to the next question. Maybe I'll say first, let me say first why I want this projection, and then we'll figure out what it is. We'll go completely in parallel there, and then we'll use it. Okay, why do I want this projection? Well, so why project? It's because as I mentioned last time, this new chapter deals with equations AX equal B may have no solution. So that's really my problem, that I'm given a bunch of equations, probably too many equations, more equations than unknown, and I can't solve it. Okay, so what do? I solve the closest problem that I can solve. And what's the closest? Well, AX will always be in the column space of A. That's my problem. My problem is AX has to be in the column space, and B is probably not in the column space. So I change B to what? I choose.
So basically, we are projecting B onto the column space of A. Maybe some kind of a basis of column space, I guess, or the closest vector, maybe. So basically, you need to project the closest, find the closest projection. Oh well.
The closest vector in the column space. So I'll solve AX equal P instead. That one I can do. Where P is, this is the projection of B onto the column space. That's why I want to be able to do this, because I have to find a solution here, and I'm going to put a little hat there to indicate that it's not the X, it's not the X that doesn't exist. It's the X hat that's best possible. So, so I must be able to figure out what's the good projection there. What's the good right-hand side that is in the column space that's as close as possible to B, and then I know what to do. Okay, so now I've got that problem. So that's why I have the problem again. But now let me say I'm in 3 dimensions. So I have a plane, maybe, for example, and I have a vector B that's not in the plane. And I want to project B down into the plane. Okay. So there's my question. How do I project a vector? And I'm really, what I'm looking for is a nice formula. And I'm counting on linear algebra to just come out right. A nice formula for the projection of B into the plane, the nearest point. So this, again, a right angle is going to be crucial. Okay, now, so first of all, I've got to say, what is that plane? To get a formula, I have to tell you what the plane is. How am I going to tell you a plane? I'll tell you a basis for the plane. I'll tell you 2 vectors, A1 and A2, that give you a basis for the plane. So say there's an A1, and here's a vector A2. They don't have to be perpendicular, but they better be independent, because then that tells me the plane. The plane is the plane of A1 and A2. And actually, going back to this connection, this plane is a column space. It's the column space of what matrix? What matrix? So how do I connect the 2 questions? I'm thinking, how do I project onto a plane? And I want to get a matrix in here. Everything's cleaner if I write it in terms of a matrix. So what matrix?
For example, A1 is the first column, A2 is the second column, and like some combination, or maybe multiple of one of these vectors as a third column.
Has that column space? Well, of course, it's just the matrix that has A1 in the first column and A2 in the second column.
Oh, okay.
Right? Let's be sure we've got the question before we get to the answer. So I'm looking for, again, I'm given a matrix A with 2 columns. And really, I'm ready, once I get to 2, I'm ready for n. So it could be 2 columns, it could be n columns. I'll write the answer in terms of the matrix A. And the point will be those 2 columns describe the plane, they describe the column space, and I want to project. Okay, and I'm given a vector b that's probably not in the column space. Of course, if b is in the column space, my projection is simple. It's just b. But most likely,
sorry, I just got distracted.
Of course, if b is in the column space, my projection is simple. It's just b. But most likely, I have an error e, this b minus p part, which is probably not 0. Okay. But the beauty is that I know from geometry, or I could get it from calculus, or I could get it from linear algebra, that this vector, this is the part of b that's perpendicular to the plane. That e is perpendicular to the plane. Your intuition is saying that that's the crucial fact. That's going to give us the answer. Okay, so that's the problem. Now for the answer. So this is a lecture that's really like moving along. Because I'm just popping that problem up there and asking you what combination. Now, yeah, so what is P? What is this projection P? This is projection P is some multiple of these spaces, guys, right? Some multiple of the column. But I don't like writing out x1a1 plus x2a2. I would rather write that as ax. Well, actually, I should put, if I'm really doing everything right, I should put a little hat on it to remember that this x, that those are the numbers, and I could have put a hat way back there, is, right? So this is the projection, P. P is ax bar, and I'm looking for x bar. So that's what I want in the equation. So now I've got hold of the problem. The problem is find the right combination.
Okay, I missed one fact. I think I was daydreaming when when he described why he had the projection
Your
of.
intuition is saying that that's the crucial.
Okay,
from geometry. Okay, and I'm given a vector b that's probably not in the column space. Of course, if b is in the column space, my projection is simple. It's just b. But most likely, I have an error e, this b minus p part, which is probably not 0. Okay. But the beauty is that I know from geometry, or I could get it from calculus, or I could get it from linear algebra, that this vector, this is the part of b that's perpendicular to the plane. That e is perpendicular to the plane. Your intuition is saying that that's the crucial fact. That's going to give us the answer. Okay, so that's the problem. Now for the answer. So this is a lecture that's really like moving along. Because I'm just popping that problem up there and asking you what combination. Now, yeah, so what is P? What is this projection P? This is projection P is some multiple of these.
Yes, okay. Since P is in this plane, which is defined for which the basis is the two vectors a1 and a2, we can safely assume that the B is some kind of a linear combination of these two vectors, these two vectors of the basis.
Right? Some multiple of the column. But I don't like writing out x1, a1 plus x2, a2. I would rather write that as a x. Well, actually, I should put, if I'm really doing everything right, I should put a little hat on it to remember that this x, that those are the numbers, and I could have put a hat way back there, is, right? So this is the projection, P. P is ax bar, and I'm looking for x bar. So that's what I want in equation. So now I've got hold of the problem. The problem is find the right combination of the columns so that the error vector is perpendicular to the plane. Now, let me turn that into an equation. So I'll raise the board and just turn what we've just done into an equation. So I'll write again the main point. The projection is ax bar, x hat, and our problem is find x hat. And the key is,
so what we need to find is the coefficients of this linear combination. So basically, how to get B from the basis of this plane.
That B minus ax hat, that's the error, this is the E, is perpendicular to the plane. That's got to give me, well, what am I looking for? I'm looking for two equations now, because I've got an x1 and an x2.
Okay, I think I got the gist of it. So the reasoning behind all this is that a times x hat gives us the formula for the plane, basically, for any vector in the plane. So basically, any vector for which a x equals this vector is solvable is vector lying in this plane or in the column space of A. One of these vectors is actually a projection of B onto the plane. So what is the additional constraint that will allow us to pick out this particular projection vector out of all of the vectors that are in this plane? This helps us. The fact that the difference between the B and this vector in the plane is perpendicular to the plane. There is only one such vector, and this vector is what connects the endpoint of B with the endpoint of B of its projection.
And I'll get to equations because, so this thing E is perpendicular to the plane. So what does that mean? I guess it means it's perpendicular to A1 and also to A2, right? Those are two vectors in the plane, and the things that are perpendicular to the plane are perpendicular to A1 and A2. Let me just...
Fine. So basically, how to find the vector that is perpendicular to the column space of some matrix? It's just to find the left null space, or the simple null space of A transpose.
So really, I have the equations A1 transpose B minus AX is 0, and also A2 transpose B minus AX.
This is right, because from school geometry we do know that there is a what's the English word? It's enough for us to know that some line is perpendicular to two intersecting lines in the plane, to say that the first line is perpendicular to the plane as a whole. This is exactly what happens here. We will take two vectors which are the basis of the plane, and we'll find the vector that is perpendicular to the both of them. And we will from this we can tell that this vector is actually perpendicular to the whole plane.
Those are my two equations. But I want those in matrix form. I want to put those two equations together as a matrix equation. And it just comes out right. Look at the matrix A transpose. Put A1 transpose is its first row. A2 transpose is its second row. That multiplies this B minus AX and gives me the 0 and the 0. You see that this is one way to come up with this equation. So the equation I'm coming up with is A transpose B minus AX hat is 0. Okay. That's my equation. All right. Now I want to stop for a moment before I solve it. And
is it though? Yes, exactly. So what we are finding here is the first one is the A transpose times some vector, which gives us zeros. And this is exactly what I said. What we are finding is that we're finding a null space of A transpose, or the left null space of A, which will be perpendicular to the column space.
And just
exactly.
Think about it. First of all, do you see that that equation, back in the very first problem I solved on a line, on a line, the matrix A only had one column. It was just little a.
This is the same shit.
So in the first problem I solved, projecting on a line, this for capital A, you just change that to little a, and you have the same equation that we solved before. A transpose E equals 0. Okay. Now, a second comment. I would like to, since I know about these four subspaces, I would like to get them into this picture. So let me ask the question. What subspace is this thing in? Which of the four subspaces is that error vector E? This is nothing but E. This is this guy coming down down perpendicular to the plane. What subspace is E in from this equation? Well, the equation is saying A transpose E is 0. So I'm learning here that E is in the null space of A transpose. Right? That's my equation. And now I just want to see, hey, of course, that was right. Because things that are in the null space of A transpose, what do we know about the null space of A transpose?
Is that it's perpendicular to the column space of A.
So the last lecture gave us the sort of the geometry of these subspaces and the orthogonality of them. And do you remember what it was? What on the right side of our big figure, we always have the null space of A transpose and the column space of A and their orthogonal. So E in the null space of A transpose is saying E is perpendicular to the column space of A. Yes. I just feel, okay, the damn thing came out right. The equation for, the equation that I struggled to find for E really said what I want. That the error E is perpendicular to the column space of A. Just right. And from our 4 fundamental subspaces, we knew that that is the same as that. To say E is in the null space of A transpose says E is perpendicular to the column space. Okay, so we got this equation. Now let's just solve it. All right, let me just rewrite it as A transpose A x hat equals A transpose B. That's our equation. That gives us X. And, oh, allow me to keep remembering the one-dimensional case. The one-dimensional case is...
No, that was the same shit. What again happened here? Ah, okay, the same stuff. Just open the parentheses and shuffle the...
little a.
Okay.
So this was just a number. Little a transpose, A transpose A was just a vector, row times a column of number. And this was a number. And X was the ratio of those numbers. But now we've got matrices. This one is n by n. A transpose A is an n by n matrix. Okay, so can I move to the next board for the solution? Okay, this is the key equation. Now I'm ready for the formulas that we have to remember. What's x hat? What's the projection? What's the projection matrix? Those are my 3 questions that we answered in the 1D case, and now we're ready for in the n-dimensional case. So what is x hat? Well, what can I say but A transpose A inverse, A transpose B. Okay. That's the solution to our thing. What's the projection? That's more interesting. What's the projection? The projection is A x hat. That's how x hat got into the picture in the first place. X hat was the combination of columns, and I had to look for those numbers, and now I found them, was the combination of the columns of A that gave me the projection. Okay, so now I know what this guy is, so it's just, I multiply by A transpose A inverse A transpose B.
What?
That's looking a little messy, but it's not bad.
Okay, is matrix multiplication associative? No, it's not. No, it's not. We can move parentheses. Or is it actually associated? Yes, it's not commutative. We can move the parentheses all we want, which is exactly the associativity principle. But we cannot change the multiples with each other, because that would be commutativity, and the matrix multiplication is not commutative.
Combination is our like magic combination. This is the thing which is like what's it like? What was it in one dimension? What was that? We must have had this thing way back at the beginning of the lecture. What did we, oh, then A was just a column.
There was a lot of numbers.
Little a transpose over A transpose A, right? That's what it was in 1D. You see what's happened in more dimensions. I'm not allowed to just divide because I don't have a number. I have to put inverse because I have an n by n matrix. But
okay, this is a projection matrix. This is not the projection itself, or rather, no, this is a projection. Yes, exactly.
Same formula. And now tell me what's the projection matrix? What matrix is multiplying B to give the projection?
This one, the underlined one.
There it is. I even already underlined it by accident. The projection matrix, which I use capital P, is this. It's that thing. Shall I write it again? A times A transpose A inverse times A transpose. Now, if you'll bear with me, I'll think about what have I done? I got this formula. Now, the first thing that occurs to me is something bad. Look, why don't I just, here's a product of two matrices and I want its inverse. Why don't I just use the formula I know for the inverse of a product and say, okay,
it's an identity matrix.
A inverse times A transpose inverse.
This is strange.
What will happen if I do that?
It's going to have the identity matrix.
What will happen if I say, hey, this is A inverse times A transpose inverse, then...
Okay, when we are taking inverses of the multiples of matrices, we are switching sides. So basically, A times B inverse is B inverse times A inverse. So what we are going to have here is A times A inverse, which is an identity matrix, times A transpose inverse times A transpose, which is another identity matrix, which is identity by identity is an identity matrix. And what we will receive is that the projection matrix is actually an identity matrix, and it doesn't do anything. Okay.
Shall I do it? It's going to go on videotape if I do it. And I don't... All right, I'll put it there, but just like, don't take the videotape quite so carefully. Okay. So if I put that thing, it would be A inverse, A transpose inverse, A
exactly.
transpose.
Exactly.
And what's that?
It's an identity matrix.
That's the identity. But what's going on? So, right, you see, my question is, somehow, I did something wrong. That wasn't allowed. And why is that? Because A is not a square matrix.
Okay.
A is not a square matrix. It doesn't have an inverse. So
why can A not be a square matrix? I understand that in this case it's not a square matrix, but what if we had... Okay, in the beginning, when we started talking about it's a three-dimensional case. We were talking about what is an example of a matrix which would have a column space of this plane. And Professor Strank suggested that we use the matrix of two columns. In terms of, when we're talking about the 3D case, it's going to be two columns each, 3 lines of height. So basically it's 3 by 2 matrix, and it's definitely not a square matrix. But what we can do is we take some linear combination of A1 and A2 and add it as a third column to this matrix, and we will receive the 3 by 3 matrix, a square matrix. Oh shoot, it still won't be invertible, right? It still won't be invertible because... Yes, exactly. It still won't be invertible because there would be no... Why it won't be invertible? Because to have an invertible matrix, what we need to have is we need to have n pivots when we are doing elimination. And if the third column will be a linear combination of the first two columns, then we will have the third row will be zeros, all zeros. Because the rank of the matrix will be 2, not 3. The third column will be all zeros. And we won't have n pivots. So basically A is by definition in this case is not invertible, because if it was invertible, then Ax equals B would be solvable for every B, because the column space of the FA would be all of the R3 in this case, or Rm in m-dimensional case. Okay, now it's all coming together.
So I have to leave it that way. This is not okay. If A was a square invertible matrix, then I couldn't complain. Yeah, let me think about that case. But my main case, the whole reason I'm doing all this, is that A is this matrix that has too many rows. It's just got a couple of columns, like A1 and A2.
Okay, I want to actually take it a pause and actually write it down why A is not invertible. Because it wasn't actually, it took me a minute to come to that conclusion by myself. And if I will be reading this lecture notes at some time in the future, I won't understand why A is not invertible. I need to write it down. Okay, so what I wrote down right now is this. So why is A not invertible in this case? Because we started with the assumption that Ax equals B is not solvable. This is the premise for the whole chapter. Why? Because if Ax equals B would be solvable, we wouldn't need all this stuff with projections and stuff like that. We just solve it directly. But if the inverse of A exists, then the equation x equals b always has a solution x equals a minus 1 times b. So then this is not the case. Thus A inverse does not exist in this case, and A is not invertible.
But lots of rows, not square. And if it's not square, this A transpose A is square, but I can't pull it apart like this. So I'm not allowed to do this pull apart, except if A was square. Now, if A is square, what's going on if A is a square matrix? A nice square invertible matrix. What's up with that? What's with that case? So this is all.
And I really don't like this explanation because A can be square matrix, but it can be not invertible. Again, as I said, you can always add another column that will be a linear combination of two other columns. It will be a square matrix, it will not be invertible, it will have rank 2 if we're talking about a three-dimensional case. But answering what Professor Strank is asking here is that if we, just what I said, if it was invertible, the whole...
The formula ought to work then too. If A is a nice square invertible matrix, what's its column space? So it's a nice n by n.
Actually, this is fun. It's fun because I just understood what he's talking about. He's talking about the fact that if we had the A was invertible, then the projection of the vector onto the vector space would be the vector itself, because it would the projection matrix would be degraded into identity matrix. And this is exactly the case, because if you are projecting a three-dimensional vector onto the whole three-dimensional space of R3, you are getting the vector itself. If you are actually allowed even to speak about the projections of the vector onto a three-dimensional space, but why not?
Invertible, everything great, matrix. What's its column space? The whole of Rn. So what's the projection matrix if I'm projecting under the whole space? It's the identity, right? If I'm projecting B onto the whole space, not just onto a plane, but onto all of 3D, then B is already in the column space. The projection is the identity, and this gives me the correct formula, P is I. But if I'm projecting onto a subspace, then I can't split those apart, and I have to stay with that formula. Okay. And what can I say? So I remember this formula for 1D, and that's what it looks like in n dimensions. And what are the properties that I expected for any projection matrix, and I still expect for this one? That matrix should be symmetric, and it is. P transpose is P. Because if I transpose this guy's symmetric, and its inverse is symmetric. And if I transpose this one, when I transpose it, will pop up there and become A. The A transpose will pop up here, and I'm back to P again. And do we dare try the other property, which is P squared equal P?
Okay, I need to write it down. I want to write this, Chen.
Squared. Okay.
Again.
And what can I say? So I remember this formula for 1D, and that's what it looks like in n dimensions. And what are the properties that I expected for any projection matrix, and I still expect for this one? That matrix should be symmetric, and it is. P transpose is P. Because if I transpose this guy's symmetric, and its inverse is symmetric. And if I transpose this one.
Okay, yes. So basically we will write down the terms in the reverse order. The A transpose at the end of this formula becomes A. The A transpose A is a symmetric product. So basically the transpose of A transpose A is the same stuff. And what we know about the inverses of transposes and the vice versa, that the inverse of a transpose is a transpose of the inverse. So basically we could rewrite this as A times, okay, let's start this from the beginning. A minus 1 A transpose equals A times A transpose times A inverse and transpose of all this central times A transpose. So the outer multipliers are automatically right. You are getting A in the beginning and A transpose at the end. What's with the center stuff? Can we write it as A times the transpose, the inverse on the outside of a transpose of a symmetric product. A transpose. transpose. And what is the transpose of a symmetric product of a symmetric matrix? Is it the same matrix? So what we are left with is A transpose times A inverse times A transpose. Exactly. So yes, it equals P. P transpose equals P. The property is satisfied.
Will pop up there, become A. The A transpose will pop up here, and I'm back to P. And do we dare try the other property, which is P squared equals P?
Okay, this is harder, I think. Not so easy.
It's got to be right. Because we know geometrically that the first projection pops us onto the column space, and the second one leaves us where we are. So I expect that if I multiply by, and let me do it, if I multiply by another P, so there's another A transpose A, inverse A transpose, can you, God, 8 A's in a row is like obscene, but do you see that it works? So I'm
okay, exactly. What he has here is that there is, here is an identity matrix. Okay, so basically this A transpose times A, we can actually add this, the parenthesis here, and here, times the inverse of it, of this stuff. So basically this whole stuff is an identity matrix. And we can just leave it out. And what we are left with is exactly P. It's A times A transpose A inverse times A transpose, which is P. So this is correct too.
comparing that, so what do I do? How do I see that multiplication? Well, yeah, I just want to put parentheses in good places so I see what's happening. Yeah, here's an A transpose A sitting together. So when that A transpose A multiplies its inverse, all that stuff goes, right? And leaves just the A transpose at the end, which is just what we want. So P squared equals P. So sure enough, those two properties. Okay. Okay, we really have got now all the formulas. X hat, the projection P, and the projection matrix capital P. And now my job is to use it. Okay, so when would I have a bunch of equations? Too many equations, and yet I want the best things. And the most important example, the most common example, is if I have points. So here's the application. These squares. Fitting by a line. Okay.
Bless you.
So I'll start this application today, and there's more in it than I can do in this same lecture. So that'll give me a chance to recap the formulas, and there they are, and recap the ideas. So let me start the problem today. I'm given a bunch of data points, and they lie close to a line, but not on a line. Let me take that. Say it.
This is interesting because I know how to do these squares using the derivative. I know how to calculate the coefficients of the line using the derivative, basically the optimization. Wait, interested what is a linear algebra approach for this problem?
2 and 3. I have 1 and 2 and 2 again. So my data points are, this is like the time direction, And this is like, well, let me call that V or Y or something. I'm given these 3 points, and I want to fit them by a line, by the best straight line. So the problem is fit the points 1, 1 is the first point. The second point is t equals 2, b equal 1. And the third point is t equals 3, b equal to 2. Those are my 3 points. T equals, sorry, that's 2.
Exactly.
Yeah. Okay. So this is the point 1, 1. This is the point 2, 2, and that's the point 3, 2. And of course, there isn't a line that goes through this. So I'm looking for the best line. I'm looking for a line that probably goes somewhere. You think it goes somewhere like that? And look, I didn't mean to make it go through that point. It won't. It'll kind of, it'll go between. So the error there and the error there and the error there are as small as I can get them. Okay. What I'd like to do is find the matrix A, because once I found the matrix A, the formulas take over. So what I'm looking for this line. B is C plus dt. So this is in the homework that I sent out for today. Find the best line. So I'm looking for these numbers, C and D, that tell me the line, and I want them to be as close to going through those 3 points as I can get. I can't get exactly, so there are 3 equations to go through the 3 points. It will go exactly through that point if, let's see, that first point has t equal to 1. So that would say C plus D equals 1. This is the 1, 1. The second point, t is 2. So C plus 2D should come out to equal 2.
Okay, I think I got it.
But I also want to get the third equation in. And
this is
that
fun.
Third equation, t is 3, so C plus 3D equals only 2. That's the key, is to write down what equations we would like to solve but can't. If we could solve them, that would mean that we could put a line through all 3 points. And, of course, if these numbers 1, 2, 2 were different, we could do it. But with those numbers 1, 2, 2, we can't. So what is our equation ax equal b that we can't solve? I just want to say, what's the matrix here? What's the unknown x? And what's the right-hand side? So this is, the matrix is 1, 1, 1, 1, 2, 3. The unknown is C and D. And the right-hand side is 1, 2, 2. Right? I've just taken my equations and I've said what is AX and what is B. Then, there's no solution. This is the typical case where I have 3 equations, 2 unknowns, no solution. But I'm still looking for the best solution. And the best solution is to solve not this equation ax equal b, which has no solution, but the equation that does have a solution, which was this one. So that's the equation to solve. That's the central equation of the subject. I can't solve ax equal b, but magically, when I multiply both sides by A transpose, I get an equation that I can solve, and its solution gives me x, the best projection, and I discover what's the main.
And I haven't actually thought about this way. So basically we are writing down that ax equals B. Not solvable. We can actually multiply by A transpose AX equals A transpose B, but X is different this time. This is solvable. And this is exactly what we're doing.
Matrix that's behind it. Okay, so next time I'll complete an example, numerical example. Today was all letters, numbers next time. Thank you.
Okay. Okay, I need a minute. Okay, so this is where I'm going to start putting all this into the flashcard application. This is actually this statement that B equals is a multiple of A. What it says is that B is in the column space of a matrix A, the matrix that only consists of A and multiples of A. It actually can be a square matrix again. So since we're talking about the 2D case here, It could be a 2 by 2 matrix, for example. It could be a 2 by 5 matrix. There was 5 multiples of it. It would still be the same stuff. It would still define the same line. And it would be still the same stuff. It would still be XA because it would still be in the column space in the same of a matrix. For simplicity, it's just A, the vector matrix, but it could be more. And exactly what we are trying to find here is we are trying to find the left null space. We are trying to find all the orthogonal to the column space of A. All the vectors that are orthogonal to the column space of A. Alright, let's start. Okay, we're going to start. Actually, I want to start the music going. That's exactly how I want it. Exactly. I'm sorry, you're probably experiencing some kind of sound issues, whether with music or with the lecture sound or with my voice. I actually didn't bother to calibrate my volume levels prior to the stream, but oh well, next time I'll do it better, I promise you. Okay, so the question is how to calculate projection of one vector onto another in a 2D case. This whole stuff goes there. Is that actually the best way to create the Yankee flashcards? Because there's too much in it for you. You will have hard time answering this question because you'll have to either you will have to sit with the paper and the pen and just try to write all this down, or you're going to have to try to devise this all in your head, and you're probably going to fail because there's a lot of stuff. You will probably be able to remember the general approach, but probably not the stuff, the nitty-gritty stuff that happens here with the vectors. How can I break it down into smaller pieces? I don't think I can. All right. Now, projection matrix in 2D case. What? Okay. What's going on here? Something's wrong. This one should be B, I believe. I don't think this is a correct derivation here. So you can either write A here or you can write A here, but it's better to write it from this point, but then you can just move the B out and leave A here. This is not correct answer. This is an error. Okay, so I'll just take this one. Actually, the interesting question is, what is the rank of P in 3D case? Can we just... What did I just do? Shit. The fuck? I can just rotate it with this stuff. I don't know how to do this. Okay. Alright. Okay. Fucking hell. We know the rank of P is 1 in the 2D case, because the rank of A times AT is 1, and then we're just dividing it by the number, so it's trivial in this case. In the case of when we're talking about the 3D case, well, I think actually this formula will stay true in any case, in any dimension. what's the rank of this matrix? Can we actually tell anything about its rank? What is the rank of this symmetric product? I don't think we can actually tell anything about this. Let's Google it. Let's actually put like this rank of symmetric matrix. Okay, this is way too complicated answer. But basically this actually implies that no, that the rank is not 1 for symmetric matrices. Okay. The next question goes like, properties of projection matrix. Okay, use case for linear algebra. Use case for projections in linear algebra. Okay, I'm going to have this just to have the general approach. I will write it exactly. General approach to derivation of projection matrix in higher dimensions. I will use all this. And then exactly the formula. projection matrix in higher dimensions. It's like I'm talking about something supernatural. The fuck, higher dimensions. I am the god of terminology. Okay, I cannot actually read this book on the stream, I think. It's copyrighted. I could actually say that this is like fair use and stuff like that, but, well, the problem is I don't have the book, I don't know the book. I'll have to buy the book firstly, before in digital format. So I will just keep reading the book. And I will go straight to the problem solving. So let's look on this recitation. Let's stop the music. What the fuck? Yeah, there's a lot of stuff to do. What the hell? Okay, let's try to find a direct out in the YouTube. Okay, I can't actually, really can't find the fuck. Ah, here it, I think here it is, yeah. Need to take a look.
My name is Nicola, and we are working orthogonal projection. Specifically, we are gonna compute the projection matrix onto the plane given by the equation x plus y minus z equals 0. So before we start, let me just recall what a projection matrix is. So you've seen this sketch here a million times already. A projection matrix takes any vector in the free space, well, in this case, we're dealing with a free space, and projects it down onto the plane, two-dimensional space, subspace of our space. So I'm going to give you a few moments to consider the problem for yourself, and
Okay. So we have a plane which is defined by its normal 1, 1, minus 1. We have some vector b. We want to calculate the projection matrix for this plane, rather on this subspace. So what is the plane? The plane is a vector subspace. Or rather, it's a column space of some matrix for which any two vectors lying in this plane are columns. So what we need to do is we need to devise a way to find a couple of linearly independent vectors within this plane. Actually, any vector that produces 0 when the dot product of this vector with the normal calculation gives 0 will be lying within this plane. Exactly. No, am I right? I think so. So we need to find vectors which produce 0 when we multiply it by n. It's actually 1, 1, 2. So the first vector that comes to mind is 1, 1, 2. It's the vector that will produce the 0 when combined with when the dot product of it is calculated with n. So we need to find another vector, and it should not be of the form n to n, to be linearly independent from the first one. Let's say it's going to be 1 and 3 and minus 4. So we have two vectors. One is 1, 1, 2, and the second one is 1, 3, minus 4. And we can create a matrix for which these two vectors will be the columns. Then we can transpose this matrix to find the A transpose, and it will give us the first row is 1, 1, 2, and the second row is 1, 3, minus 4, for example. Now comes the fun part. We need to, I think we'll start with calculating the central multiplier of this, of the formula for the projection, and it's going to be the inverse of A times A transpose. So first we need to calculate what is A times A transpose is. Times 1, 1, 2, 1, 3, minus 4, which is I really hate multiplying matrices, you know. This is really not a job for a human, this is a job for a computer. This is 1, this is 4, this is minus 2, this is 4, this is 10, this is 2, minus 12, this is minus 10, right? Yes. This is minus 2, this is 2, this is minus 10. Oh, and this is 2, 2, 4, minus 12, right? Yes. So we received a symmetric matrix, which kind of tells us that we were right, because we know that the product of the matrix with its transpose must be symmetric. So we have this matrix, it's 3 by 3. And now what we are doing is we are more matrix multiplication, because now what we are going to do is we're going to multiply it by, we're going to find this its inverse. Now we're going to find this inverse. This is fun. Not. So to find its inverse, we must combine it with an identity matrix and use the Gauss-Jordan elimination procedure. So we're writing 1, 4, minus 4, 4, 10, and minus 10, minus 2, minus 10, minus 12. And on the right side we are writing the identity matrix. And we are starting the elimination procedure. So first of all, we are subtracting 4 times the first row from the second row, which gives us 0, minus 6, and minus 2. Right? Yes. Right. So, and here we're going to have minus 4, 1, and 0. The last, we are going to add 2 times the first row to the third row. Shall be 0, minus 2, and minus 16, I think. That was going to be 2, 0, 1 in the identity matrix side next. Is it right? Looks right to me. Okay. The next step is we are going to add. Okay, we are going to actually flip. Yes, what we are going to do is we are going to change places. We are going to exchange. We are going to permutate. We're going to change the places of the first, of the second and the third row. 0, 1, because otherwise we would have to multiply by 1/3 and we would get the fractions in the matrix, and I really hate working with fractions, so we are going to use 0, minus 2, minus 16, 2, 0, 1, and the third row now will be 0, minus 6, minus 2, minus 4, 1, and 0. So the next step, we are multiplying the second row by 3 and adding it to the result to the third row. 1, 4, minus 2, 0, minus 2, minus 16. And the third row now will be 0, 0. Oh, 3 times 16 is 48. So what I'm going to do is I'm going to use... This is actually quite retarded because I'm going to use the Ruby, which is not actually anywhere near a good choice for working with matrices and for doing mathematics, because it's quite slow, I believe, at least. Okay, so matrices are created as such. Okay, I cannot actually calculate the projection matrix from the get-go, so let's do it step by step. So the A is the matrix new. I can actually do it like this, I think. So the first is 1, fucking hell, what the hell is going on? It's 1, 1. The second row is 1, 3. And the third row is 2, minus 4. Okay. Alright. A transposed is A transpose. Alright. 1, 1, 2, 1, 3, minus 4, exactly. Now we're going to symmetric product will be A times AT, which is 2, 4, minus 2. Okay, I fucked it up. It should be 2. 4, 10, minus 10. Yeah, well. And -2, -10, 20. Why 20? Because minus times minus. Okay. This is why I want to do this on the computer, because I'm not a great arithmetician. Okay. Now what we're going to do is we're going to take the inverse, not regular matrix, which is trying to tell me what exactly? Why is it? It cannot be such. This matrix must be invertible. Why though? Okay, let's try to find what it's trying to sell me. Yeah, there will not going to be a lot of discussion on this side because, well, not a lot of people actually use Julia. No, I don't have Julia installed. Alright, let's review this stuff. 1, 1, 1, 3, 2 minus 4. Exactly, transposed, yes. Yeah, because it should be A transpose times A, not A times A transposed, so. Yeah, much easier, right? It's very simple. This is something I actually could do by hand, but I don't have to. Again, you can see there's fucking fractions everywhere. I hate fucking fractions. So now what we are going to say is we are going to calculate A times sim inversed times A transposed. Alright, so this is the projection matrix. The first row is 2 sevenths, 3 sevenths, and 1 seventh. Then the second is 3 sevenths, 26 35ths, minus 3 35ths, 1 seventh, minus 3 35ths, and 34 35ths. This is my final answer. Let's see what you can tell me about this. I'm eager to see it.
Again, okay. So in lecture, Professor Strang derived in meticulous detail the formula for the projection matrix. So it was given by the following slightly complicated expression. It's A times A transpose inverse A transpose, where A is a matrix that somehow encodes the subspace we're projecting on. In particular, A has as columns A1, A2, I'm going to ignore them, a basis for the plane we're projecting on. So essentially what we need to do is find two such vectors, extend the plane, and start computing with the matrix. Yeah, this is fairly straightforward. One choice that works, for example, is 1, negative 1, 0 for the first column, and 1, 0, 1 for the second column. Okay?
Yeah, these are much better choices than the ones that I have devised. Still, he has to come to the same conclusion,
okay.
the same solution that I did.
So, in the formula, I guess the slightly more complicated combination is A transpose A inverse. So let me compute that first for you. Okay, so A transpose A is a 2 by 2 matrix, and it's not so hard to figure out it's 2 and 1, 1, 2.
Shit, this is the skill.
Now we shall invert it. Using the familiar formula, 1 over the determinant, 2 times 2 minus 1, 3. And so we switch the diagonal entries, and we flip the signs of the diagonal. Right. And therefore, the projection matrix given by the following product of matrices.
But I'm starting to think that he won't come to the same conclusion as I did.
1/3
Yes, exactly, because I actually fucked up the choice of the vectors. Because I would choose the vector with a -4 as the last. My second vector was -4 as the third component, and this is a mistake because it should be just 4. So let's try it again. Alright. So A transpose is A transpose. Symmetric product will be A transpose times A. The inverse. Much simpler, right? And then I will just A times sim in times A there's T. Yeah, this is probably what he's going to have.
Okay. I'm going to carry out this multiplication in a humanly fast fashion. So I'm just going to write down the answer, which is 1/3 to 1. Right. So what?
So what was this?
Right.
Okay.
What you can do now is
Calm down, man.
you can check whether this answer actually makes sense. One thing you can do is just, well, projection matrix is supposed to take the normal to the plane down to 0. So you can just multiply P and the normal vector 1, 1, negative 1, and if you get 0, maybe you've done a good job. Another curious thing that I would like to point out here is, so you see we had lots of freedom of choosing the matrix A. I mean, we could have chosen any 2 columns that span the subspace, that spans the plane. The beautiful thing about it is that in the end we get the same answer. Right. So I hope there will be many of you who would say, hey, there is an easier way to do this problem, and I'll agree with these people. So let's see what would be an easier approach. Well, let's go back to the sketch here, right? And let's make the following observation, that any vector is a sum of 2 components. The first component is this projection onto the plane, and case, onto the normal vector to the plane. So in the language of linear algebra, this is just B equals to projection onto the plane plus its projection, we're going to call it Pn, onto the orthogonal complement of the plane.
Shit, I'm starting to get the vibes that this is going to end up with this the weird stuff that I actually did not quite understand when we were talking about the how the null space and the row space are the orthogonal complements of each other, and each vector B can actually be, from the Ax equals B equations, can be split into these two projections basically. Now I understand that they were just projections, the one onto the null space and the other one onto the row space. And if B is in the row space, is in the column space, I think. Oh shit, I think I messed it up. I was talking about the column space, now we're talking about the row space. Or, I mean, the other way around. We were talking about the row space, now we're talking about the column space. So basically we have the projection onto the column space, and we have a projection onto the, exactly, and we have a projection which is, what is the normal in this case? The normal in this case is the null space, is the left null space. I mean, if we actually would write it down the other way around, if we would write it down so that these vectors were part of the row space of the matrix, we would probably realize we could actually make the same derivation. Just the normal wouldn't be the left null space, it would just be the null space of a matrix.
Okay, I'm gonna suggestively write here the identity matrix so that you can immediately read off a matrix equality associated with this. Equality here is the identity equals, and therefore the projection matrix is just the identity minus the projection matrix also.
How the fuck did it happen? Sure, I follow this stuff.
So that you can, okay, I'm gonna suggestively write here the identity matrix so that you can immediately read off a matrix equality associated with this. Equality here is the identity equals P,
Why though?
and therefore the projection matrix is just the identity minus the projection matrix all to the normal vector.
Okay, I need to take a break. again, why does this happen? Why can we say that if we have the equation tells us b equals pb plus p and b, and then we just multiply, we have to multiply both sides with it, or rather not, we can say yes, exactly, ib equals pb plus p and b. Oh yeah, exactly, because the matrix multiplication is distributive in regards to matrix addition. So basically we can rewrite this stuff is identity times b equals, within the parentheses, p plus pn times b, which exactly tells us that identity matrix equals p plus pn, and we can say that p is identity minus pn. This is right.
And much easier to compute.
This is correct.
Well, for two reasons. First one is that projecting onto a one-dimensional system is infinitely easier than projecting into a higher dimensional system. And second, we already have, immediately you can read off from the equation in this place all the normal vectors. So we don't have to derive these guys. Like, we don't have to do what we did here. Okay, so firstly, En will be n transpose n inverse n transpose equal to 1 n transpose n inverse. This is just a number. It's 1 over the magnitude of the normal vector. So that's then the magnitude squared. That's 3. Okay. Right. The answer here is third 1 negative 1 1 negative 1 and negative 1. Right. So yeah, in order to get the projection matrix. Yep. Oh, thank you. And in order to get a projection matrix, we just subtract from the identity expression, and you can confirm that we get the same.
Oh, okay. I think I can actually write it down. So I'll call it alternative way of calculating projection onto a subspace when dimension of a normal to a subspace is less than dimension of the subspace itself. What I can actually do is I can screen this part. Actually, now scrap that. But the first question I will say is ask myself is a connection between projection onto the subspace and projection onto the normal to a subspace. is quite easy. Right, and the next step. So here I won't use any screenshots anymore. I'll say that alternative way of calculating projection matrix for a subspace. And I'll just write here that you can, calculate projection matrix onto the normal to a subspace. Then subtract it from the identity matrix of correct size. Okay.
Alright, I think we're done.
That's right. This is a transcript, right? This is not okay. Why is it Dave? Wasn't Dave? All right, the hard part, problems. Okay, suppose A is a 4 by 4 identity matrix with its last column removed. Ah, okay, I understand. 1 0 1. Okay, 1 0 0 0 1 0 0 0 0 1 0. Okay, so the last column is all zeros. Project B equals the 1 2 3 4 onto the column space of A. What shape is the projection matrix B, and what is B? So the projection matrix is a square matrix 4 by 4, because otherwise you won't be able to project anything onto it, right? Onto the column. What is the column space of A? It's a 3D space within the fourth dimensional space. The column space is basically a 0 vector plus 3. Okay, actually, the column space is R3 within R4, because actually any three-dimensional vector can be expressed as a part of this. So basically, any three-dimensional vector is a part of the column space of this matrix A. So what do we need to do? We need to transpose this matrix, for example, for starters, which will be 1 0 0 0 1 0 0 0 1, and the last row will be all zeros. To calculate the column space, right? Yes, exactly. Why is the column space now? Okay, because we might need the solution to some equation. Alright. So AT times A is, it's going to be a 3 by 3 matrix. Is it? No, it's gonna be 4 by 4. Exactly, it's gonna be 4 by 4. 1 0 0 0 1 0 0 0 1 and all zeros here, and then 0 0 here 0 1 0 here 0 0 1 0 there. All right. So we're going to have 1, going to have 0 0 and 0 here in the first row, then we have 0 1 0 and 0. Okay, the last column is all zeros. This is obvious. Alright, I'm going to have 0. This is 0, this is 0, and this is 1. And all zeros again. Yeah, this is symmetric matrix. It's definitely a symmetric matrix. What's the inverse of this matrix? Does it actually have an inverse? I'm not sure. I don't think so. I don't think it actually has an inverse. It doesn't have any pivots, that's for sure. Okay, let's check ourselves. We can say that A is a matrix such that with numbers 1 0 0 0 and then 0 0 0 and the last one is 0 0 1 0. We need to transpose it. And then we are going to find the symmetric product. Exactly what I had in mind. Does it have an inverse? It should not have an inverse. Yes. Okay. Because it should be one column removed, not one row removed. Exactly. So in this case, they just changed places. The transposed matrix and the original matrix, they changed spaces. And so now we are multiplying okay, and now we will have the 3 by 3 stuff. Is it fine that we have the 3 by 3 stuff? Oh, you know what? It's okay. It's okay because we will receive the 4 by 4 matrix later when we will multiply by A and then by A transpose. So yes, it's going to be 3 by 3. Okay, 10. Okay, the other way around. Ruby coder here. A equals A transposed and A transposed equals 10. Exactly. A t times A. Right, exactly. And this is an identity matrix. So the inverse will be still the identity matrix. So if I use this same, this is A still, and this is A t. And we are getting this stuff. So the 4x4 matrix with the last column and the last row all zeros. Let's write it down. Okay, let's write it down accurately. Okay. And I need to project B on this. And the P is going to be P times B. Is it 1, 2, 3? Oh. Oh. No. Okay, it's going to be 1, 0, 0, 0 plus 2 times 0, 1, 0, 0 plus 3 times 0, 0, 1, 0. And the last one is irrelevant because it's going to be all zeros and I just don't care about it. What I'm going to have is 1, I'm going to have 2, 3, and 0. 1, 2, and 3, and 0. Yes, exactly. Okay, the second one. If p squared equals p, which we know is right, show that identity minus p squared is identity minus p. Okay, this is the answer that I know. The last part is the something that the guy from recitation already told us. And if P projects onto the column space of A, then I minus P projects us onto the left null space. Because it projects us onto the normal, to the, well, you know. Okay. I minus b times I minus b, and we know that this is distributive, so we can tell this identity times identity minus p minus identity minus p times p, which is identity minus p minus identity times p plus p squared. Okay. Identity minus p plus p, which is identity minus p. Okay, let's take a look at the solutions and the way of thinking that was used to come to this conclusion. This is the fun fact. So if you are projecting something, come on, how the fuck? Oh, okay. Yes, this is exactly the case. Imagine that you are projecting some kind of a vector, a 3D vector, onto the 2D plane, the coordinate plane. So basically the basis for the plane that you are projecting on is 1, 0, 1, 0, 0 and 0, 1, 0. So basically x and y and the z is 0. And what you are doing is you are projecting some vector onto this plane. And the projection will be just your components of your vector, of your x and y components of the vector. And the z will be just discarded. So the same thing actually happened here. We are projecting the four-dimensional vector onto the 3D space, the whole of 3D space, and you just remove the coordinates and that's it. Okay, yes. Exactly. Correct. Okay, so I have finished the part from reading the suggested reading, which I'll do out of the screen time. And tomorrow I'm going to start doing the projection matrices and least squares, the next unit. Thank you all. See you tomorrow.